So, hi, hello, and a warm welcome here from Karl. Together I am joined by Vision Electric Superconductors with the persons Wolfgang Reiser and Viktor Stark. Wolfgang Reiser is the CEO and founder of Vision Electric Superconductors, and it's a great pleasure to welcome him here in this interview. And together we want to take a technical deep dive into the superconductivity concept and into electric busbars. We are joined by Viktor Stark, who is head of sales and marketing for Vision Electric Superconductors. Together with myself, Karl Rabe, we were introducing a radically new data center concept to the OCP Foundation. We were actually selected to present our superconductive data center within the OCP Summit in November. And today we take the time and the opportunity to really explain what is superconductivity and how is this working in the data center. Okay, so here you see our concept for a 100 megawatt data center to the right, and this is what we call the EOS data center. EOS stands for ecologically, open source, and superconductive. And Wolfgang Reiser will now start and introduce us to the actual base concepts for superconductivity. Now Viktor will introduce us to the base concepts of superconductivity.
Yes, thank you, Karl. So this is the first slide here. I would like to explain what is the difference between superconductors and copper or aluminum material, which is normally used for data center busbars. So why do we need superconductors? And superconductors, they have a lot of benefits compared to this used materials today. And the major benefit and the most important benefit is that you can conduct very high currents within a very small space. So if you see this picture in the middle, that's a comparison between a aluminum bus bar with 20 kiloampere and a 20 kiloampere superconducting bus bar. So the small piece lying above the aluminum bus bar is the 20 kiloamps superconducting bus bar. So you can here see the relation between the sizes. And the same as on the right picture, it's also a relation between copper and superconductor. The second, also very important benefit is superconductors do not have any electrical losses with DC. Therefore, it is much more efficient than normal systems, and the higher the power consumption of a data center is, the more efficient superconductor becomes. Since you do not have any thermal, electrical losses, it also means you do not have thermal emissions, which means that you have, or you don't need to cool down that much, and that also saves energy. What is really important and has become even more important in the last years, what we see is that Scope 3 emissions is a big issue in the data center industry. Regarding that, superconductors is the best thing because since it is compact, lightweight, it is just easier to transport it to make a construction. And we developed also a modular system with the ability to reuse these modules, but this is something we will explain later on.
Great, thank you. So you explained the benefits. In terms of the obvious question, is this cost-wise, is this more expensive, or are superconductors more expensive?
Yes, but it depends on the view. What is more expensive today are the capex. So you have to invest the money in the superconductors, which is 2 or 3 times more expensive than a comparable aluminum busbar, for example. But on the other hand, you have almost no power losses, and this leads to much lower operation costs. And therefore, if you look at the total cost of ownership, superconductors are even today more attractive than the standard technology.
Okay, thank you.
And therefore, one point, we have a big potential to use economies of scale effects. So superconductors are not that expensive because the material is too expensive. And of course, there's also some potential in the optimization of the production process. But the most thing is we need just to produce a bigger amount to get lower costs on that. And therefore, one day, I think that superconductors will be as cheap as aluminum or copper today.
Okay, thanks. So obviously there is one major difference, right, in terms of the operational temperature of the superconductor. How do you cool your superconductor?
We use high temperature superconductors, and they need an operating temperature of 77 Kelvin or below. And that's something we can realize with liquid nitrogen, which is normally easily available and also not expensive.
Okay, minus it is, or 77 Kelvin is around minus 210, 209 degrees, right?
It's minus 200 degrees.
Okay, yeah, thanks for the non-physics out here.
Yeah, I'm not sure
Okay.
what it is in Fahrenheit.
No, okay, but we'll stick to the metric system here, or yeah, to Kelvin, or just as comparison at this degrees. Okay.
Yes, I agree with that.
Okay, thanks. Good. Then I think this is it for the questions. Okay. So Victor, please explain us, a bit of the history and where we are at today with superconductors in production.
Yes, if you look at this table here, we have a comparison between the superconducting performance of the tapes within the last 10 years. And as you can see, the production is more efficient. The carrying current capacity is more than doubled. And also the production volume is increasing. So I think that superconductors, although it is quite new to many people, it is a technology where many companies in the industry slowly realizes the really huge potential in there. So superconductors, and this is something also not everybody knows, is already used for a long time in MRIs and in magnets. So
MRIs,
it is not.
please explain. That
Yes.
is this
These
is
are, these are the medical devices. How can I explain them to which? Yeah, I don't know how to explain MRIs.
this magnetic Röntgen, right? Is it that?
Yeah.
Yeah.
Yes.
Yeah.
That. So the thing is that those superconductors, they have to be cooled far below those 77 Kelvin, and you have to cool them with helium, which is not that easy. The high temperature superconductors were discovered around 30 years ago. It's maybe 40 years ago. Meanwhile, it's 1968. Interesting
86.
thing is
1986.
1986. Yeah, right. Was discovered by two men, Georg Bednorz and Müller, and Mr. Bednorz is and Mr. Müller both won a Nobel Prize in Physics for this discovery. Only 1 year after the discovery, which is very fast. So I am proud to say that Mr. Bednorz, he is supporting us still up to date. And yes, that's something I just wanted to say.
So you have a direct connection to the inventor.
Yes, we have.
Perfect. So what are
yeah.
so some of the applications you see on the left? Can you explain us a bit deeper what some of them are? So you have this is not only theoretical, and this is real. There are a lot of things that actually you and Wolfgang and Vision Electric superconductors have put in production, right?
Wolfgang, would you please say some words about the application examples here?
Okay. Of course, there are a lot of applications where superconductors are give advantages to. So we first concentrated on industries, and we installed a 20 kiloamp system in a chlorine plant here in Germany, just to demonstrate that that superconductors are industry ready. In the same time, another system was running in Essen, in the grid, in the city grid of Essen, about to show that superconductors are also ready for installation in the grid. It was in the city grid, and parallel to that, some other installations showed that superconductors give a lot of advantages, especially to machines, to rotating machines, which was installed in a wind turbine. So on a lot of different fields, and you see some more fields here on this slide, on a lot of fields, superconductors can give a lot of advantage just by eliminating power losses, by reducing outer sizes, dimensions, and, for example, on the wind power, reducing a lot of weight. So these are mainly advantages in applications.
Okay. So one question in terms of the impressive improvements for the superconductor as a material, right? You were talking about the tapes. Do you feel that this development is going on, and when do you believe, in your experience, is like a tipping point for the industry to make this even more available?
Yes, okay. A few years ago, when I started with superconductivity, we had tapes that were able to carry about 150 amps, which is much more than any copper can take on the same cross section. Today, we are in a region of 1000 amps. So that multiplication of about a factor of, let's say, roughly factor 7 or 8 was done within a short period of time, and that is the same, the same growth of the performance of such tapes, which was observed for semiconductors. So I think that this development is going on for at least the next 10 years. That means we will see more and more superconductors in the development that are carrying a lot of current and that are going to be more cost efficient. So this trend is going on, definitely.
So we're just at the beginning. Great.
We are at the beginning, and we are at the beginning of a tremendous development. Superconductors just left laboratory a few years ago and entered industry. And we are now in a phase where industry is scaling up on the production of superconductors, and vision electric superconductors is transferring and transforming using superconductors and transforming them into applications and which are used in industry and in grids.
Great, thanks. Okay. No, I think that that covers this. Okay. Good. Moving
Shall I
on.
continue on the next slide?
Yes, please.
Sure. Yeah.
Okay.
This is more familiar. This is more my turf. I see, lighting loads, electric loads. This already could be potentially a data center.
This is for the data center. This slide is a slide of Intel, which is about 15 years old, and Intel in those days made a investigation. What will happen if all the different energy steps are just cut out for the power supply of a data center? And if you look to a data center, you have a lot of energy conversion steps. You are starting with energy coming from the power lines, from the power grid. You convert them first into a low DC voltage to feed your battery, and then in case the battery is needed, they are transformed back from battery into a transformable AC, going over to the facility level, maybe on large data centers with several other conversion steps, and finally going then to the power supplies of the servers. And during these conversion steps, all the conversion units are not running on optimum efficiency, but in most cases on part efficiency, and therefore you have quite some high losses on the conversion rate. So Annabel Brett of Intel in those days just made a study cutting out all the different power conversion steps, and she found that this will save about 15% of the power losses, which are normally there in a data center, and 15% on the power losses. That is something which is not that small. The bad thing on this was that in those days superconductors were not really available. So if you're going to a higher power, then the current which is then on low voltage and which is then higher, the power loads and power losses are eating up the advantages of reducing the conversion steps. And this was then the reason why this was not realized for large data centers. In the meantime, superconductors are here, and superconductors are the missing link. They conduct very high currents on zero losses, zero emissions, and therefore superconductors are the material which will be used for DC powered data centers. So this is an advantage, combining direct current supply and superconductivity for a new design of power supply for data centers.
Great. So you're saying that superconductive data centers are really a lot more efficient, and they uncover efficiency that is not even measured currently, right?
I'm not saying that. This is an IEEE study done just 2 or 3 years ago, which came to the same conclusion. Worldwide, there are about 20 data centers running on DC, smaller data centers. One I have visited is in Stuttgart. The other one is close to Zurich, a green data center. And all those data centers on relatively small power have showed that DC data centers save energy by not having these extra energy or power conversion steps in between. So this is not my conclusion, but it is demonstrated by a lot of others. But the missing link is that we have introduced into DC data center superconductors, which allow them to grow. And we are looking for hyperscale data centers in a range of 100 megawatt. We can go down, let's say 20 or 40, but we love to be 100 and higher.
That's the reason is that superconductors are so powerful, right? So there's not really a limit in terms of transporting energy. Right?
That's right. That's right. If you look to this small bundle of superconductors coming out here on this conductor, this is actually something which can carry today between 30 and 40 kiloamp, 40,000 amps. And if you compare that without any losses, and that is very easy to bring high currents on low voltage to any place in a data center.
Okay, thanks all. That was it. Big thank you to Victor and Wolfgang for supporting me on this, for putting this interview, this deep dive together. This is the end of our generic part. We will continue very soon with the actual EOS concept of our 100 megawatt data center, which we will present at the OCP Global Summit in November in San Jose. So stay tuned on all our channels or on LinkedIn. We will announce that soon. Bye now.